Bem-vindo, estudantes, a Noce na Mathematique. I don't know. I don't speak enough. But I learned, yeah. All right. Stop. Okay, for today, we are going to be continuing on and finishing finally 5.3. We don't have a whole lot to look at today. If there's no questions from the assignment, that was a cough, right? Okay. All right. For this is going to be the last little section that we're going to look at. Now, no, it's still 5.3, 5.3.3, the very last one. Our first little subsection today. I just want to kind of look at what we've talked about. We talked about the first and second parts of the fundamental theorem. It says that here's how you evaluate a definite integral. Here's how you take the derivative of a definite integral. Those are the things that we looked at. Yesterday we looked at all those applications where we know that you can work out the unit by just multiplying by whatever the delta t or delta x happen to be. Today, our last little step, we are going to be looking at the integral as an accumulation function. The integral as an accumulation function. Blah, it's long. Okay, we are looking at the integral as an accumulation function. What does it mean to accumulate?
Build up.
To gather, right? To get more, build up, however you want to word it. When I think of accumulation, I think of precipitation, right? Naturally, snow, probably, snow accumulation. Okay, now as we're looking at this, we're going to jump in immediately with an if-then statement. If f is continuous, and I'm going to be more specific. I'm going to say if f is non-negative. If f is non-negative on some function a to b, could be 0. Definitely could be 0. Non-negative does include 0. If f is non-negative on a to b, then we can define a function. Just commit. Just pull it all out. Just go quick instead of listening to it crinkle the whole time. Just do it. Just pull it.
Why can't we just say positive?
Because positive doesn't include 0.
Oh, what?
Positive numbers is 0 a positive number?
Is 0 negative?
It's not negative.
Then what is it?
Non-negative includes 0. If I wanted only non-negative numbers, that's 0 and every positive. If I wanted only negatives, I'd say non-positive numbers. Say greater than or equal to 0, but it's easier to say non-negative. But you're right, it could be greater than or equal to 0, absolutely. Anyway, if f is a function that's always greater than or equal to 0 on a to b, then we can define a function as follows. We're going to define our function, capital F of x. Now, this is the first time we're going to see the integral as a function. We'll say this is the integral from a to x of f of t dt. Now, I really want to highlight here, the t that shows up in there is merely a placeholder, a dummy variable that we're working with. If you want to call it f of x dx, you're still not wrong, but you have to understand that there's a difference between f of t and capital F of x. Okay, as we look on this function that we've defined, this is it, where we're going to say that 0 is less than or equal to, I guess not 0, I'm sorry, a is less than or equal to x, is less than or equal to b. So x has to live between there, which allows us to accumulate, And in the most basic sense, what we typically think of the integral as giving is area, right? Like that's how we saw it first. We saw that it's not always area. It depends on what the context is. But I'm okay if we just say it allows us to accumulate area.
Which allows the function to accumulate area, or?
Yes. I'm going to say us, actually.
What does that mean?
It means we can keep adding up more and more area. We're accumulating it, right? Now, we'll look at what this actually works out to be. If, however, the function does happen to fall below the x-axis. the function falls below the x-axis. We can still allow for the idea of negative area. We can allow the idea of negative area.
Elaborate on that.
Yeah, we definitely will, for sure. Now, the idea of negative area doesn't really make sense, right? Areas are never negative. All that this tells me is that when I'm thinking out context with stuff, and we'll even draw a graph to kind of sort this out, it allows us to deal with this negative area. Let's compare first just to make sure we understand what this accumulation function is really doing. I'm going to have two graphs here, just so you know. Let's say it goes from A to B, just like regular. And this time, let's say it is all positive. And I might have a function that does something like this. Now, I'm sorry?
Should we write this in our book?
I would draw this, definitely. Where did I say x has to live? Between A and B, right? Now, I wish I had a good animation for this. I don't. Let's just say there's x. And I'm going to draw that bar up, and I'm going to shade this little area. Now, I'm going to let everybody catch up to make sure that we all have it drawn.
Hey, are you recording?
I am.
You can pause.
I saw.
Oh, did you tell him?
No, I saw.
No, it's right here.
She's doing her job. I can't see that.
All right, for this thing, if I knew the actual value of x, how would you find this area?
The thing integrals.
The integral from where to where? If I wanted the area of this
A to
a to x, right? If you knew what x was. Now, what this function allows me to do, this capital F of x, if I don't plug anything in. I wish I could do this with a slider, but imagine that I could physically grab this x and start pulling it to the right. Would I be getting more area?
Yeah.
You might even say that I'm accumulating that area. Okay,
Oh, no.
for this,
Brilliant.
with this thing, it wasn't really a joke, it was,
You thought I was
okay, for this thing, is this above or below the x-axis?
above.
Above. This area would be signed as positive then.
Oh, you're not erasing the area. You just.
No, I just wanted to make sure I could put a plus in there. It's a positive area. It's above the curve. Now, if we compare and contrast that with the following graph, I'm going to make it a little bit longer there. We'll say here's A and B. And this time I'm going to have a graph that might start up here and then kind of hang out down here a bit. I think it's clear that there are two very different areas. Now, I don't care where x is. I'm just going to say it's here for now. If I wanted to accumulate this area, I'm going to pick two different colors when I do this actually. I'm going to pick red as hot, right? Typically, red, fire, warm, positive temperature. Okay,
Yeah, it is.
so here we go. This area up here. What do you think that is?
Hot.
It's hot, as in its temperature is positive or negative?
Positive.
Positive.
Scale are we using?
Oh, wait, are we doing?
What's its
Yeah.
pH balance?
Yes. Okay, here's my positive area. Now, the second, however, that I jump underneath here,
I don't think.
brr, because that area underneath is what?
It's cold. Not hot.
It's not hot,
negative, though, is it?
it's negative.
Because of what?
It's frozen, its temperature is below 0.
We're going
Negative
up.
42 degree Fahrenheit and Celsius are the same.
They are.
Yeah, that's crazy.
Okay, so for this thing, again, my function, hold on, let's work out an idea here. My function, if I started sliding this thing to the right, I would be gaining area. Now, this is a weird idea because you're gaining a negative area, right? If you went all the way over to B, you would have a negative net area. That's what the integral gives us, the net accumulation of whatever it happens to be. On last night's assignment, you saw the net accumulation of sales or the net accumulation of distance. That is called the displacement or the net accumulation of sales. Henry.
So, when you're talking about the slider stuff,
Yep.
are we probably going to do things like find the net, like, increase of area or whatever, like the speed at which the area is increasing?
So So the speed at which the area is increasing would just be the derivative of it, which we've already done problems of that type. We'll do problems of this type today even. Sean.
So if you take the negative 5 and you subtract 15, is that gaining or is it subtracting? Or is it losing?
I would say you're losing.
Okay,
So
then why for this then?
this is a weird idea to get used to, but remember, it's just there. For this, turns out though, there's something even more valuable to this.
Oh yeah.
This allows a shortcut. This allows a shortcut.
Wait, what's this?
This whole idea. This allows a shortcut for multiple multiple integrals. Multiple integrals. Now, specifically when we do this problem that we're going to work together, I'm going to present it in a way that I don't normally present these problems. And you'll see the difference. For this thing, just a curiosity question. If the amount of area that I've gathered is capital F of x, let's say for this function, the amount of area is f of x.
Okay.
Where's the max of f of x going to happen at? Let's say that my f of x function, and you can write this or not, I don't really care. If it goes from a to x of some function f of t, this is a function, and we'll see this as a function in fact. Where's the maximum of this guy?
X.
At x right here?
Maximum. Oh.
Where's the most area happen? From a to where?
0.
Beta. There.
Right there, isn't it? From a to 0, that would give me the biggest positive area.
Yeah.
What if you went for the minimum? Where's it the smallest?
The negative.
How far would you have to let x go to get to your minimum?
Infinity.
Can't go out to infinity though. How far do I go?
B.
To b. If I went all the way to b, that would be my minimum. Now, the logic behind that is going to get it's going to get tough to kind of think about. Let's do one problem real quick. Here's what I want us to do. On this example, and there's only one here with 3 parts. What I want us to do is find the area. Find the area between the x-axis. Between the x-axis and the graph of y equals the sine of x.
Could you also say just a function?
So if I just said find the area, you couldn't say
What's
the graph is a picture, right? Because we don't really have a good way to think about area unless you can imagine this picture. There has to be some area enclosed. I want us to find the area between the graph and the x-axis, specifically from x equals 0 to, from x equals 0 to, and then this is where it's going to be different than our normal problems. First one, I want to know what's the area from x equals 0 to x equals 3 pi fourths.
This is like question A.
Yep, it's really all 3 about this. And this is where it's going to be different. Because I also want to do b, and let's just say b is at x equals 5 pi thirds. And c, we'll go ahead and say is 2 pi. Now, for this, how would you even begin this problem? And we're just going to let somebody tell us how they would begin that problem. Who is it? Kayla! Did anybody else know it was going to be them? Yeah. All right. Kayla, if we're working this thing out, I could draw the graph if you want to, and we'll use the graph to investigate it afterward as well. I assume we'd start with A. How would you find the area from x equals 0 to x equals 3 pi fourths underneath this? So I wouldn't just want to draw it, because I'll tell you right now that the graph of sine looks something like this with a smoother curve. That doesn't really help. Like, it might help to make sense of, but can you give me a calculus type of expression that would allow us to find the area from something to something of some function?
Integral
The integral from where to where?
from 0 to 3 pi points.
Okay.
And then sine x. Would it be dt or dx?
Dx, because the x is here. Okay, does everybody agree that we could do it that way?
Yes.
Now, here's where this problem becomes a pain, though. Because on B, James, what would you do?
Do the same thing. The integral from 0 to 5 pi thirds of sine x dx.
Well, he tried to
5
get
pi
you, but
thirds.
you got him.
Of sine x.
Yeah, I got
dx.
you all the way.
You showed me you understand the problem. You got me good. Okay, Kathleen, how would you do this last part? Okay, now looking at this, I think this is a natural way to see it. But here's the thing. Notice that each of those functions, all three of them, I would have to do 3 integrals. And it's not going to be terribly hard, but it's going to be time intensive. You're going to have to do 3 integrals. Unless we can all agree that if I start at 0 and then I just slowly start sliding that value of x right, it's like I'm accumulating more area. To solve this problem, why instead of doing 3 different integrals, don't we just find a function that allows me to accumulate this area?
Oh my god.
I don't have to do 3 integrals.
So just 0 to 2 pi?
Not 0 to 2
No,
pi
0 to
even.
X.
Check
Oh.
it out. I'm going to let this function, f of x, be my accumulation function. And I'm going to let this thing be the integral from 0 to any value of x that you might pick.
X. Oh my
Sine,
god,
yeah,
that's
of
exactly
x.
what I said.
Of sine x dx.
That's great.
Now, this is this shortcut that we were talking about. Notice I have multiple integrals that I would have to evaluate. Maybe I don't really have to do multiple of them, though.
It's crazy. It's like instead
What's
of-
the antiderivative of sine x?
He says it's like just reading it. Yeah.
Negative cosine.
So it's like when he does that.
This is negative cosine of x from 0 to x. Now, in this case, notice we didn't use a dummy variable. I don't want you to get confused. Instead, could I have said sine of t dt to use a dummy variable?
I would hold that.
Because I might be concerned that you're going to get goofed up plugging in x for x. Maybe you won't, maybe you will. If you think that this part's confusing, where do you plug this x in for?
X.
X. If you're okay with doing that, I'm fine with it. It may be easier for you if you see that and go, what? Now what do I plug this x in for?
T.
A t. And it feels more natural to place an x or a t with an x than it does an x with an x. It's just a weird little piece, but if you're okay with x, I'm okay with x. Okay, this is the first or the second part of the fundamental theorem that we're doing right now.
The second.
This is the second part. The first part would say take the integral. Or, sorry, take the derivative. How do you do this then? I plug in
F of b.
f of b, which is just negative cos x, minus
Oh, wait.
Negative cos 0.
negative cosine of 0. Now, you're absolutely right, Kathleen. I heard you say it, but I want to pick on somebody else here. Henry,
Yeah.
what is negative cos x minus a negative cos 0?
You just added, but
What's it add to?
cos what? Yeah, cos of 0. That's just 1.
Thanks, bud. All right, so as we're here.
Did you write before I said it? I was looking at you.
What?
Did you?
No.
Okay.
Okay, as we're looking at this thing, this function right here is my shortcut. And I'm going to make sure that we have this. This function accumulates the area.
Can you just distribute that negative? Or just cos x minus 1? That's
You cannot. Because it's only attached to the cos x, because we did this one.
gotcha.
This function accumulates area from x equals, or from, yeah, I'm going to say from x equals 0 to x equals whatever I choose.
So it's like we found the general, or, I don't know.
We have literally found a function that allows me to find the area at any point. Just like when we learned the derivative, we found a function that gives me the slope at any point. This is a function that gives me the integral at any point. The exact same. The derivative could be a function or an instantaneous rate of change. The integral can be a function or an instantaneous area, or whatever context you might have with it. Now that I have this statement, I'm going to slide to the right. And let's go ahead and reinvestigate A. If I wanted to know 0 to 3 pi fourths, it's as easy as taking f of 3 pi fourths. This function is the integral from 0 to x, right? I just said let x be 3 pi fourths. This is the integral from 0 to 3 pi fourths. And you could do it as an integral, or I could use this handy function that I already have. Would you rather do the integral or just plug it into a function? I definitely don't want to do it both ways because we've already done all this work. It'd just be this, except instead of x here, Petter, it'd be 3 pi fourths. Which you'll have lots of time to get that practice today on the assignment. I want to use the function now because it's so much easier. When you plug in, this becomes negative cosine of 3 pi fourths plus 1. And all of a sudden, here we are in trig land. What's the cosine of 3 pi fourths? Is it root 3 over 2?
Root 2 over 2.
Okay, here's our unit circle. Here's 0. Here's pi fourths.
It's root 2.
Here's 2 pi fourths.
It's root 2 over 2.
Here's 3 pi fourths. Is it? It's negative root 2 over 2. Negative root 2 over 2 plus 1. I don't need the, I just needed it here. Plus 1. What do we get when we do that?
Root 2 over 2 plus 1.
Okay, can you simplify that for me?
Heck yes.
Wait.
Will you simplify that for me?
2 root 2 plus
Root
1.
2. It's root 2.
2 root 2 plus 1. Or no, 2 root 2 plus 2. All over. Oh, wait.
Wait. Over root 2.
Yeah. That's
Okay.
root 2.
2 plus root 2 over 2.
So
That's what I said, yeah.
Units squared, since we're talking area in this particular problem. Was doing that one calculation easier than doing the definite integral? I think so. I think it was a lot easier than doing the definite integral. Now, notice, I can go from 3 pi fourths and I can just start adding up area. Sure, I'll do that. On B, I'm going to find f of what value am I going to for x?
5 pi thirds.
5 pi thirds. I'm sorry? Okay. This becomes negative cos of 5 pi thirds. 5 pi thirds
That's just the same
plus
as
1.
Is 2 pi thirds.
Is it the same as 2 pi thirds?
Yeah.
I hate when you say is it. Or when you
Yeah.
say sure, like
Sure is my yes.
sure might seem like okay,
No.
but there's a better answer.
Yeah, like it's average, but.
Yeah, that's
Sure,
what- yeah,
that's your
what-
opinion on that matter. Okay, for this
Yes or
thing,
no
This
question.
is a lot
more
of
kind of useful question. What's the cosine of 5 pi thirds?
Same as the cosine of 2 pi.
I don't believe you.
Right?
Mm-mm.
Isn't it?
Okay, do you guys agree that at negative pi thirds, it's like if I started here, which way do I fall if I'm going negative?
Down.
Pi thirds, that's like 60 degrees. Would I be farther right or farther down?
Down.
I'm farther down at this point, right? This is 1/2. Specifically, it's positive 1/2. Sean, I said it's not the same as 2 pi thirds because it's the same as pi thirds.
No, but you could.
2 pi thirds lives over here, which is a negative cosine value.
Oh, right, right.
'Kay.
See, I thought the unit circle was out of pi and not 2 pi.
Oh,
So
okay.
I got confused.
All right, that would do it.
Aw.
Okay, with this, we can take a unit circle quiz someday. It will not be today, but we do need to make sure we know them. You have to know these. Cosine of 5 pi thirds is 1/2 is what we know it to be. Negative 1/2 then, plus 1 is what?
1/2.
1/2.
Are we
The
gonna need to
area here is 1/2 unit squared. Sorry, James?
Are we gonna need to know tangents on the unit circle for the
Yeah. I mean, just no sine over cosine. You have it. Okay, I want you guys to do C for me.
That's not always easy.
F of 2 pi. And while you're evaluating out this, I'm going to go ahead and get a graph up. If you're watching this video at home or on the road, I want you to pause it and try to work through this. Graph. Notice, as we're looking at this thing, it has symmetry, right? Sine always looks the same over a certain amount of time. A period, its periodicity is 2 pi. We've gone 0 to 2 pi, which means this red area up top is the exact same as this area down here. The total net area then would have to be exactly 0. Now, with that said, This is its net area. What if I asked you to find the total area, like the real area?
Infinity.
I don't agree with
Zero
that.
to infinity.
You just double it?
You would double it. Now, depending on what it is, you would have to be able to answer this question. Let's go ahead and actually do this question.
Oh, then we can take.
What is
pi,
the
so-
real area?
So pi and double it. So f of pi and double it, right?
Okay, Petter had a good idea. He realized that this point right here, although it's not labeled, what is this?
0.
No, pi. This is pi right here. It's where sine goes back to being 0. What Petter recognized is, hey, if we want the actual area, couldn't I just take twice the integral from 0 to pi, which I can just write as f of pi, and get it? Now notice I wrote f of pi instead of the integral from 0 to pi, but they're the same thing. This function f gives me that value. So let's just see what it spits out at us then. 2 times, well, we have negative cosine of pi plus 1. What's the cosine of pi? 0. Are you sure?
Yeah.
Are you sure?
No, that's probably have to.
Wait, pi.
It's negative 1.
That's what I said.
Negative 1 plus 1 is 2 times 2 gets me 4. The exact real area is 4 units squared. Compared to the, what did we answer on C? The net area. Okay, now what we're really doing is there's a couple different ways that we could do this problem. The important kind of follow-up comment that we're going to make, I do want to talk really quickly, and we'll see this next section as well. Last comment when we're comparing net versus total or real stuff. As we're looking at this, yes.
You have to draw the graph.
You don't need to draw the graph unless you want it. Okay. I want to know what's the difference between displacement and distance traveled.
Displacement where you
Say
end
it's like
up.
a couple
Where you
times.
Like
end
where you
up
end up,
versus
and then like distance is
what
like.
you do to get there.
Okay, so specifically, and we'll see this again in an upcoming section, I'm not sure when, but displacement is the net change in position. This is the integral from a to b of v of t dt. If you give me velocity and integrate it, that gives me the displacement. The net displacement is how we wrote it the other day, but I think I'm okay with just saying the displacement. Okay, if we compare that to distance traveled, and I want to think about this using this sign picture up above. I already have the picture of sine. There's certainly possible that a particle's velocity is modeled by the sine function. Lots of stuff moves in waves all over the place. Okay, if you wanted to know the total distance traveled and this was a velocity function, how would you account for where it turns negative? What could you do to make that become positive? The integral from a to b of the absolute value of the velocity gives me the total distance traveled. And because if you imagine graphing it, the absolute value would give us this thing. And then I would just have this extra red area to count. Okay, distance traveled is an absolute value expression. Displacement is not. We will see this again. You are not going to be forced to remember this right now. I'll even scroll down so you can see that a little bit better if you're looking. Distance traveled is absolute value so that we can account for, well, if it was negative, just take the absolute value and it becomes positive again.
So if we did like f of 2 pi, would we put a absolute value bar, and could that give us the real area?
So we could have, and there's actually a property that we would use instead, which we'll see in the next section. If this were velocity, absolutely you could have. Okay, for that, that's all I have for 5.3.
Wait. Could you go back to what you were?
I'll just write the homework here. Your homework. This is homework 5.3.3. I think we might get a full week of homework, guys.
What?
I don't know what page this is on, but it's 5.3, and I want you to do odd AP problems. 415.
What's your favorite vine?
Grapevine?
I don't have a favorite vine. Okay, good luck.